Douglas West is an encyclopedic book. It has like, but you can keep it with you, and it's a very cheap book. You can even buy the hard copy. There is an Indian edition that you can buy. So just to mention it again, I'll just screen once. Yeah, but it intersects, okay, and a lot of things I say in a different way, like we set up these trees through, in a matroidal approach, we said, and so on, min max. A lot of things are not there, and there are a lot of extra things which I have not discussed. Okay. Anyways, just to make it clear, the book's name is Douglas West. Okay, graph theory. Introduction to graph theory. Okay, so let us start. Okay, so just 1 minute. Just give me 1 more minute. There was 1 second. Just pause the. No. Today there's no counting class. Next week I'll. Yeah. Today only 1 hour class. Okay. Yes. Yeah. Right. Okay. So we have done counting tree. This is what we have done. Counting trees. Okay. So obviously we know what trees are. Trees are let me not write that. We all know what they are. Connected graphs with no cycles. Okay. On n vertices, connected graphs with no cycles are called trees. And there are so many other formulations. Connected graph with minimum number of edges, connected graph with, or rather a graph with maximal number of edges but no cycles. And so many formulations can be given. That's the beauty of this definition. Okay. But we have counted it. Okay, so number of trees on n vertices. So if you have n vertices, then the number of trees turns out to be n to the power n minus 2. Okay, we had done a very interesting kind of proof, right? By every tree we gave a sequence. Okay, yeah, let's not review that because we have recorded it. And so the thing, and this is the beginning of many interesting counting problems whose answers is n to the power n by n minus 2 can be done via, by using trees as a bridge, okay, in between. But that is for later, maybe what it is. Okay. But now today, so let me just write this. So we have basically connected graphs with no cycles. I'm just writing it like this because I will now want to generate. This is a question that I asked myself when I studied this topic. So connected graphs with no cycles. Okay. And just to make one thing very clear, when we say on n vertices, I mean numbered vertices. So what I mean is that this is different from this. Okay, because you see 1 and 3 are neighbors here, 1 and 3 are not neighbors here. So this, it's labeled graphs. Okay, but these two graphs are in some sense the same, in some sense, right? But roughly you can feel what that sense means, but we are not identifying those things. We are counting them as, if we identify them, then the problem becomes very difficult. Okay, and then you need some group theory to do it in a sane manner. But we have simple labeled trees. Okay. Yeah. Now moving forward, the next thing that we want to do is we want to remove this word connected and just want to count number of graphs with no cycles. Okay, so let me make a definition so that we can talk about this very easily. And so graphs with no cycles. That's all we are demanding from here. Okay, graphs with no cycles. Okay, graphs with no cycles are called forests. A very nicely chosen, wisely chosen name, right? Forests. Okay, and what we are interested in is the number of forests on n vertices. Okay, so please think about this while just give me 1 more minute. Yeah, just think, because we know this answer n to the power n minus 2, can we somehow use that to find graphs with no cycles? Okay, we can think about that. So obviously there will be many more. There will be many more of them, right? But is there a way in which we can count them? So we are interested in number of forests on n vertices. Okay. So for example, I mean, I don't really need to give an example because you understand what it is because you've already seen this for trees. Is if n is equal to 4, then this just this 4 dots, 4 vertices, no edges. This is also a forest, no cycles. Yeah, this is one example. Certainly, there are many more, and there are many more, right? You can just join all of them, and obviously, I should number them. Yeah, I should not. I should number them. Yeah. So today we want to first start with counting the number of graphs with no cycles. We have already counted the number of connected graphs with no cycles, okay, which are connected and have no cycles, the special graphs, the trees. But now we are interested in graphs with no cycles. They may not be connected. Hmm. Okay. So from each of the tree, you can delete an edge. Uh-huh. Yeah, but will you get all the possible forests in that way? So your idea is to, let me just write it, pick, no, but then the number of vertices, okay, let me write. So pick an arbitrary, so the goal is here to count the number of forests on n vertices, okay? And you are saying that pick an arbitrary tree on n vertices. Yeah, that's not it sounds like a good idea. Arbitrary tree on n vertices and delete some or all of the edges, right? This is your idea. Okay, just please confirm. Okay, let's give ourselves a minute and see if this is correct. I feel there is something wrong with this. I'll not say, let's think about this and see. First of all, is the question clear to everyone, those who joined late also? Okay, we just want graphs which have no cycles. Okay. See, problem is that when you pick an arbitrary tree, right? When you pick an arbitrary tree, then it has n minus 1 edges. So you can say that you can delete any subset of those n minus 1 edges. So maybe that should be pointed out to make it very clear. Any subset of the n minus 1 edges. That is good. And how many ways are there to choose this? 2 to the power n minus 1, right? So ideally, then the answer you are saying should be this. So so already we have n to the power n minus 2 trees. Okay. And when you pick a tree, picking a tree, and there you have n minus 1 edges, and you delete some subset of them. So you can delete 1 edge, 2 edge, you can delete, there are so many choices, right? So there are 2 to the power n minus 1 choices, edge of edges to delete. So this many trees, sorry, this many forests. Is this argument clear to everyone? And does it sound correct to everyone? So 2 questions here, please just make it very clear. how would you build it? Yeah, that is thing. Oh, but that's right. But it will get so this, but this way will also get complicated because okay, I mean four, okay, even for four, right? You would have to decide. So just saying one edge or two edge is not enough, right? You have to decide which um, which of the four are in one component, which of the four, you know, which of the four are connected, and like what is the partition? Like you hear the partition is there are two and two, right? So even if you go for two edges, there are many ways in which you can do that, right? So you have to consider all partitions of four, of all partitions of the set four, and then you have to build trees. That also gets very complicated. Yeah, so that gets pretty complicated. Yeah. Yes. Which graph? Last one. Then this method will not work. Why? No, but there is no cycle. No, but this is also counting. So for this he will get, so this in this method, he will get this because he's taking all subsets. So empty subset is also there when where he does not delete anything, right? No, but he can, but why cannot he get this? Because he will get this as a tree, right? This is a tree already, right? So this he will get in this, right? And then he will not delete any edge. So he'll get this as a forest. It's a forest, and he will get this in his counting, right? In this method, yeah. But the problem in this method is not that it is missing something, it is the opposite. So this is don't want to call it hint, but just that this seems to me an overcounting. Not because I know the answer, but just because of the very method, it looks like an overcounting. This is an overcounting. He has overdone something. Can anybody spot? And to spot it, just make sure, tell you, just run this method again. Just understand that you understand this, what is being done, right? So just to give an example, if this is 1, 2, 3, 4, then from here, from this, he can, for example, you can delete this two, so he can get this 1, 2, 3. This forest. This is a forest, or you can delete only one, right? And you can get this forest, and so on and so on. There are so many ways. I think this is an overcounting, or yeah, it is an overcounting. Can anybody spot why it's an overcounting? This method, actually, the method that Ritam has suggested, this actually is used, but it requires some advanced theory of something called exponential generating functions. Okay. Yeah, you get a sort of a something called a Catalan type recurrence, um, which needs exponential generating function to be done gracefully. Okay. Yeah, that we will not discuss. Maybe when we do lattice counting, which we are doing there, when we do Catalan, then there we can discuss it, and later on. This is called Pittman's method, I think. I'm not sure the name. But anyway, this is an overcounting. Um, um, No, don't delete the vertex. You're not allowed to delete the vertex. Hmm. Yeah, but you're kind of getting there. See, actually, see, from one tree, it looks correct. If you start with one tree and you make these deletions, then this method looks correct. But think about, think about some other tree, right? You could have started with some other tree and still gotten the same thing. That is where the problem is, right? Let us see this now. I think people have got it, but I'll say this clearly. Yeah, you can get this in other. I think you can also prove this is wrong in some other ways. This seems to be too big, even as a number. Okay, it seems too big, but I'll not contest that now. I might be wrong. That's a very loose. We'll be lucky. See, the point is that, see, from here, um, I think so, right? I think you can get the same tree or same forest, sorry, in from two different trees, and that's why it's an overcounting, right? So if you remove this one, no, am I? No, I think I'm wrong, right? Yeah, no, wait. I think no, this answer is not correct, but I think I'm wrong. Yeah, so is it possible that you get the same forest from two different trees? Yeah, then it will be an overcounting, right? Huh? Yeah. No, but we have to take one also, no? We have to start with the tree with n vertices. We can't, we can't. No. But still, you are. That's no. But you're. I mean, what I was saying is right. We can still see what we can get is from a different tree. We can get the same thing. Yeah. So one has to be very careful here. Yeah. You see, from this is a different tree, and you understand what I'm trying to do is uh, 3, 2. Yeah. So they were different. So let me draw a bold black line just to see the different. Yeah. Yeah. So you see, 4 and 1. This is a different tree. These two are different trees. Yeah. But you can understand, right? I can delete this 4 and 1, and I can still get this. So you delete 1, 4. And here you're deleting 1, 2. So, but you are going to count this as different, right? Because you are starting with n to the power n minus 2 trees this way. So this is an overcounting. Is it okay with everyone? Just make sure, because once you get these fundamentals right, then a lot of theory becomes easy, and you don't even need to know a lot of theory. Then you can start reasoning and solving problems as they come in the test and so on. But these simple things, okay. So this is an overcounting. Fine. So this is an overcounting, but it's a good. I think it's a good approach. Um, yeah, and I don't think that it is a strategic overcounting. There will be, I don't know how many trees you can, from how many trees you can get it. I don't think you can do any division in principle and so on. So what is the other way? What should be the other way? Number of number of forests. Actually, this is a question that is not very difficult, unlike the tree question. Yeah, the tree question that we solved n to the power n minus 2, that is a very original question. Okay, like that question cannot be asked in an exam without hints. That is because it's almost impossible that you will be able to think of that encoding that one did, right? That's very hard to do. But This is a kind of question that is very askable, assuming that the tree thing n to the power n minus 2, number of forests on n vertices, is not a difficult question to answer. So what Rasuvu has said is he tried to go from trees on n vertices to forests on n vertices, and it did not work. But I think if you go in the reverse way, it can work. So any ideas if that sparks any ideas? It didn't work. I mean, at least we couldn't make it work. But can we go in the reverse way? So maybe the number of vertices, I don't know, but just from forests to trees, I should just say. Can we go from forest to trees? We want to count forests. How? First, you should say how. Yeah, then we can say, right? Yeah, if you no, yeah, that's right. If you add edges, then that's again the approach, that kind of approach that you were saying. That is that way it will be a menu to one thing again, just like this deleting was menu to one kind of. Yes, right. But we don't want to. No, that I do not think will work. We'll have the same problem. But we can do something smart, something different. Uh, so what are the ways in which we can go from forests to trees? So you see, a forest, as I've said, as we know, a forest is just a graph with n vertices, not necessarily connected. Yeah, no cycles. That's all we are looking at. But here is just one observation that would usually be made in a regular course about forests. Yeah, the main thing is that a forest may not be connected. Yeah. But obviously, it has obviously connected components. Connected components, right? What do we mean by this? Just take it roughly, the pieces that are connected. Yeah, the connected pieces. Okay. Yeah, in any forest you take, so any number of vertices you take, I'm not numbering the vertices, number of vertices you take, you don't want to form a cycle. Now, if your graph is not connected, then it will be broken up into pieces that are connected. Right? It could be like this. So there are two pieces, you see, two connected components. One can define them precisely and then prove that they form a partition, they are disjoint and so on, but it's understandable. Okay? Two pieces. So these two pieces are the trees. These two pieces are the trees that we are looking at in this particular forest. Let's say this tree is there and there is this other tree. How can we make a tree from this forest? So remember, our goal is to go from forest to a tree, because we know how to count trees, but we don't want to add edges. We want to do something else. Yes. Then actually that becomes complicated. That's where that was again the earlier approach, kind of. Yeah, what you were saying. Just as another hint. Okay, so if those are joined late, I have also changed the time, so maybe there was some problem. I will record it and send it. Okay, so but yeah, try to follow from here. Okay. Anyways, so let me just say so the point is that if you sit with this question for, let's say, half an hour, and you just for just count by hand, okay, for n equal to 1 2 3 4, you will unmistakably, I am sure you guys would see a pattern like we saw in the trees. Okay, and the pattern you would see, so I'm telling you because you would see it, but just work it out yourself again. Okay, and see the pattern that you would get, and then be able to guess would be, maybe not a good color, would be, so on n vertices, remember, it is n plus 1 to the power n minus 1. Now I want someone to prove. Now it's not hard, meaning that now just we need one small trick. So the answer is this, okay, n plus 1 to the power n minus 1. And this is a pattern that you would see if just like, so that's the reason why when I was doing trees, we didn't jump to the answer and try to prove it. We actually kind of discovered what the answer should be. And that is, again, something that you can do again and see that it's this. But then it's a matter of proving. So you guys can kind of feel, right, if you do this, if you expand this using binomial theorem or something, if you know, you would see, you would get a complicated expression, and that is the kind of answer you would maybe get if you do it by partitioning. Okay, I'm not sure, but we don't want to do it in that. We want to do this. What is this answer suggesting you? It is a number of trees on something. So we will no, it was n to the power n minus 2. Yes. Yeah, but it could have many components. But yeah, that's right. We have to connect these components. Yeah. But you see, so the claim is, yeah, that's what it is. The claim is that number of forests and vertices is this. But can anybody say clearly what is this? Means my claim is that we already know what this number is. This is already number of something on something. Yeah. Yes, right. This is already, so this is very clear. Right? This is number of trees. Yeah, number of trees on n plus 1 vertices. Exactly. This is just what we need. Okay. Now we just need to show. So now this will suggest what you need to do from a forest to go to a tree. Exactly. You have to just add a vertex, but what else? You add a vertex. That's right. So step 0, a forest on n vertices. Step 1, add a vertex. Add a vertex, label n plus 1. Now what do we do next? No, that's right. I connected with all the components. That's right. I think that's what we have to do. But how do we do it? We have to be a little careful, right? Otherwise, we may end up with the same situation. Like, getting, I don't know. Let's see. So let me label this because now it's a little more serious to label it. Important. 6, 7, 8. And the ninth one comes in. So n equal to 8. If you say connect, How do you connect this 9 with these two components? How do you decide? I think that is something that we must connect with one of the leaves. Okay, any of the leaves. But then there are choices involved. And we can't afford choices. Or can we? No, maybe you're right. No. We can't afford choices, right? Because then the same forest is going to lead to several different trees. Is that right? Does everybody see this? If we connect this, if you say this leaf, and let's say connect this with this, then you're getting from this one forest, you're getting this one tree. But from the same forest now, you can get a different tree if you just say connect it with the leaves. Now this is a different tree. You will always get a tree. Don't worry. You will not get cycles. That's not the problem. The problem is that you are getting from same tree, you are getting different forests. No, you are getting different forests, right? But we don't want this, right? We want that from one tree, I should get one forest. Simple. I suppose everybody agrees to that, right? We want from one tree, we want one forest, and from that forest, we want just that tree back. We do not want this. Otherwise, the numbers will not match, right? No, so I'm making a mistake again, right? This is wrong. What I meant to say is from same forest, you're getting two different trees. From one forest, you're getting one tree. And from the same forest, you see, from the same forest we have a different tree on the screen here than from the previous one. But we do not want this. So how can we resolve this? So we have to make a decision, right? We have to make a very clear decision. See, I do not think it has to be connected to a leaf. I do not think it has to be connected to a leaf. But you have to just make a decision. I mean, you cannot allow choices. The choices are the problem. Yes. So we need to stipulate, we need to say something here so that there is a unique way to get the tree from this particular forest. Uniqueness is needed. From this particular forest. That's right. Yeah. We want from this forest exactly one tree so that the numbers will match. Yeah. No, our trees are not rooted. Rooted trees are something different, slightly different. No. For us, there's no root. Yeah, that is also a problem. That's also a problem. Just like, yeah, that will not work. Just like Rastoglu said, take the leaves, means he took the minimum degree, but then there are more leaves, and usually there will be a lot of leaves. So let's try this. Well, how about we just say that you just connect it with the biggest member of that component? Simple, just keeping it simple, right? Just connect it. So you pick this, you have this n+1 lone vertex. We want to get a tree. Just simply connect it with the biggest member of component 1 and connect it with the biggest member of component 2. Just this much. That's all, nothing else. Let's write this. I'm not saying this is correct. Let's see. This should be, hopefully it works. So add edge from n+1 to largest labeled, just to be very clear, vertex of each component. Now we have, now at least, I mean, now we know it should work because the number is same. The number will match. Right? Okay. So in this way, at least what we are getting is from a forest, we are going to a tree on n plus 1 vertices, right? So from forest, and this forest could also be a tree, mind you, okay? That can be a tree. So from a forest on n vertices, we are going to a tree. We have only shown one direction, okay? And that also we have not shown if, yeah, let's say tree. We're going to tree on, I should, n plus 1. So meanwhile, you guys can think if this is correct or the reverse direction can be said or not. So, yeah. So certainly from one forest, I am going to one tree. Yeah, that is certain that we have, right? One forest. N plus 1 vertices, yes. Sorry. Right. One tree. Yeah. So from one forest, we are going to one tree. Now, what are the next tasks that we must check? What are the next things that we must check? That's right. Reversibility is the most important. Yeah, is the most important and shortest way to, you know, certify that this works. And one can do it in slightly other ways also, but that's probably the best way if we can. Yeah. So what we will try to do is to see if this is reversible. So what does it mean? So I don't want to say it in terms of bijection and so on, inverse map. Just this is combinatorics, we can just say. So we want to, so next thing is to check reversibility. Okay, so let me say clearly what this means here, because sometimes we just forget to check something. Yes, the first thing that is that, see, this is what we want to show. We want to show that number of forests on n vertices is equal to number of trees on n plus 1 vertices. Okay. See, forests understand trees better than they understand numbers, something like that. So this is why bijection principle works, because sets with these decorations, these are sets with decorations, right? They understand this decoration language better than they understand numbers. They don't understand what n plus 1 to the power n minus 1 means. Okay, so we have to just basically, it's just a matter of changing language. So what we see, the point is that from a given forest, we went to a given tree. Okay, so let's say that f1 went to, should we say a function? Let's not say a function. Okay, f1 went to t1. Okay, we now want to give first thing to do. I'm just being very, try to be very pedantic, but it's something that sometimes we miss. Okay, we just show that there is an injective map and there is a similarly map in the other direction, and it is different things that go to different things, but that is not enough all the time. Okay, in the sense that, yeah, that will not be enough unless you do more. But in any case, let me say clearly here. So the first step is to describe a reverse process. That is the very first thing. Describe a reverse. Okay. Now this should be enough to understand, but to make it very clear, what we want to say is that we have a clear way in which we went from this forest to this tree, right? Now we want to describe a process which will take some tree to some forest. Okay, but more than that, this tree should go back to the forest that it came from. Just describing a way to go from this right hand side to left hand side is not enough. Okay, you must go from the tree So that the tree that came from some forest, it must go back to the forest it came from. Okay, that is important. Okay, so every tree must go back to the forest it came from, or it must go back to a forest it came from. Yeah, that's what. Okay, if you just show that, then you can convince yourself then the both sides have the same number of members, number of forests this side, number of trees that side, the same. Yeah, so now we can. So first, if what I have described is making sense, and the second, to actually think of a reverse. Thinking of a reverse is not difficult, but we should do it. That's right. Yeah, that's no, not remove its. Yeah, you are right. You are right. Remove its neighbors. Um, 1 minute. If you take the highest labeled vertex, yeah, you must remove its neighbors. But then what I'm saying will not be correct. 1 second now. Yeah, so we would like to, obviously, the reverse should be just to remove all neighbors of n+1. See, we have to do this, right? Yeah. Yeah, we have to remove all the neighbors of n+1. But then there is a problem. Because, I mean, yeah, can any... We just remove the edges. Yeah. Sorry, we have to remove, no, we have to remove all the edges of n+1, just means it's coming out from n+1. Because obviously we want to isolate. Yes, that is right. No, so so example in this one, so we went from this forest. Yeah, so we know what the forest is here, right? It is 8 vertices, which are 8, and the black edges are the edges of the forest. We had the forest, we took 9, that's n+1. We added the 2 red edges and we came to this tree. Now you have this tree, and so that's the way forward. And to go back, uh, you just take this, for example, you have this tree and you remove these red edges. Yeah, you remove the neighbors, or you remove the edges coming out of 9, coming out of n+1, right? And that way you go back to the forest that you came from. Yes. Yeah, basically I think it should be enough to just say that you remove 9. Yeah, then the edges also go away. That's right. Does it sound okay to everyone? Because then we go forward and then we can also come back. Right? So we are able to go forward by this process, and then we are able to come back by this process, by the reverse process that we have described. No, but then there is still some problem in this. So we have not yet shown that in this way you can attain every tree on, and we have not shown that, right? We have not shown that you can attain every tree. on n plus 1 vertices in this way. So we have not shown this. Okay, we need to show that every tree on n plus 1 vertices can be attained. Oh, we have not shown this. 1 minute. Let's think about this. Yeah, does everybody see, right? We have not shown this. Wait. Yeah, we have not shown that you can get every tree in this way. And actually, you will not get every tree in this way, right? For example, I mean, how, so yeah, so this something is wrong. Yeah. So if I give you a tree like this, wrong in the sense that this is essentially the idea of the result, but maybe then the result that I'm stating is not correct. We have to maybe say something called rooted forest, but don't worry about that. I think we don't need to define so many things, but this is the idea. Okay. Yeah, but so for example, let me show why I am wrong. So we have this, and the question is, how would you get this tree? You would never get this tree. So this is same labelings. In particular, we have one. To be precise, we have 1, 2, 3, 4, 5, 9, 8, 7, and 6. Okay. Is there a way in which you can ever get this tree? From our forests, right? Because the only way, I mean, the only way you will get it, no, you cannot get it, right? Because you're going to take the biggest member. Yeah, so just think of, just take 2 minutes and think about, let me also just think about where I'm going wrong, or what should, how, I mean, in the sense that the idea is that, but you have to correct the technique. We have to correct the statement of the problem actually. Yes, right. So this is essentially the method, but what is wrong is that it's not correct in the sense that the statement of the problem is not correct. The statement of the problem has to be changed slightly to say the number of labeled is already there, okay, but the number of rooted forests, number of uh, rooted rooted forests. Yeah. So what does this mean? Well, this is a little complicated and not necessary for us. So rooted forests means that every rooted forest should mean that every component. So this is the forest that we had, right? Yeah. Forget about the 9. If this is the forest, right? So every component has a root in the sense that, but this is something different, okay? So basically another decoration that we're giving, okay? So every component that we get, every connected piece, that every tree that we have in this forest, it has a special designated member, okay? And this basically makes the problem simpler. Otherwise, then it's a more complicated question. So the answer is, so I mean, at least we have shown, at least, so just check that we have shown that the number of forests on it is this, it's less than this. So that's not, it's not a bad thing already. But in any case, it's not what we set out to do. Okay, but we realized it that it's wrong. So basically, my point is that you have to root. So your forest in which you have rooted. So this is a rooted, and let's say this. So this is a particular forest. Okay, now let me make this concept of rooted very clear. Okay, so this is a forest. Okay, this. Okay, this is a forest. Yeah. So I think the reason why other people's methods were not working was because there is no clean answer. Okay, the answer will necessarily be complicated, I suppose. Okay, but let us see what we can say. Okay, at least, but this method is what is used to at least do this problem. Okay, so this is the forest. Okay, rooted at 3 and 7. Okay, this is a forest that is rooted at 3 and 7. Okay, now my point is that when you say something is a rooted forest, I mean, this is a very important concept. Rootedness is important later on, but that's more into algorithms that it is important. We root the trees because just to make it clear sometimes that, okay, we are starting the search, depth for search, so on, from this particular vertex, okay? Because trees arise out of analysis of algorithms, okay? Because the recurrence relation of an algorithm leads to a tree. It's even called tree recurrence, and then you solve it using, I mean, while solving it, this model of tree is useful. And then if you take this other forest, so this is the same, so these two are the same forest, these two were the same forests, but now they will not be if I say that this is a forest that is rooted at 4 and this is a forest that is rooted at 8. Okay, so these two are now different forests. Okay, this is a forest. So these two were the same earlier. Okay, but now we have put more qualifiers. Okay, so this is a forest rooted at 4 and 8. These two are not the same. Yeah, they are, as you can understand, with this new notion of equality where we are also taking care of the rootedness, they become different. And there's no need to say that, no, there's no need to think that this is an absurd thing to do. Okay, because as I said in the very beginning, right, if you remove the labels of the trees, then a lot of trees that we were considering different will become the same. Okay, so that's just a matter of what you want to do, and what context you're using it, and so on. Okay, but all these concepts, but just the concept, just the theory of labeled trees and labeled forests without the rootedness is very elegant and captures the last part of things. But in this particular problem, that will actually make the problem difficult. Okay, so now these two are different. These two are different thing. Okay, these two are different forests. So now our answer will be correct. Now, if you want to count the, this is something that I can leave as an exercise also, but let us do it. Number of rooted, if you want to count the number of rooted forests on n vertices. Yeah, that will now be equal to this. Okay, again, let me just describe the method and now leave it to you to show that, you know, you can, every tree can be gotten by what we did. So the problem that was happening is that we were not getting every tree, right? Because obviously it was doomed from the beginning. I don't know why I was trying to make it work. Okay, the problem in the sense that we were joining with the largest member, right? But obviously we could have not got the other trees in which, you know, this 9 is joined to 1 and this is joined to 6 and everything else remains the same. We could not have gotten them, right? So this obviously was not correct. But if we say the number of rooted forests, then the steps are very clear. Then the n plus 1 vertices, the n plus 1th vertex comes in and you join it, you know, you join it to the roots of the components, obviously, right? Now we have a very clear choice to make, a clear, unique choice. Okay, you join it with the roots. Yeah, join it with the roots. So it comes in, Please try to complete this. Okay, join it. I think it's a good exercise to do. Join, but show that it actually that you can get all trees in this way. That's important. Okay, join n+1 with the roots of the tree components. You know, the I'll just say the components, just components of the forests. Yeah, now it's very clear. Okay, of the forests. So just to execute it here, you see you will get different trees, and that's how you get all the trees. Okay, that's how you will get all the trees. But the trees will not be rooted. So don't, okay, the trees you get will not be rooted. That's, so don't make that mistake. Okay, let's see. Okay, so you add the 9. When you have this 9 and you want to execute what we have described here in this case, then this 9 would be joined in this case with this, because again, that's the obvious canonical clear choice to make, unique, clear, canonical, everything, right? Choice to make. You get this tree. Now this is a tree you get. Now you forget about the root. Okay, it's basically just, it almost seems like the definition of rooted is just to make this work, but the rooted concept is important in any case. But if you're executing it here, then obviously you can understand that now it will be, maybe I should have done this with red, but yeah. Yeah. Then when you do this, then obviously you join it with this and this. So you see from this, but don't think from the same forest, no, because they are different forests, right? They were different forests, right? They were different rooted as rooted forests, they are different. Okay, but they, and so that's why we are getting these different trees. These two trees are obviously different. In this way, you can understand, you can get all trees. Yeah, try to write it out. You can obviously get all trees, because any tree you take the n+1th. Yeah, so remove all the edges of n+1 and designate the neighbors of n+1 to be the roots, right? Designate the neighbors of n+1 to be the root. Simple. And so you don't get just a forest, but you get a forest with the chief members of every component, with the roots. Okay, and this way you can get all trees, because from any tree you can get this rooted forest. Yeah. So then this is correct. Yeah. Otherwise, this is not a simple problem. I do not think this is a simple problem. Yeah. In any case, as we learn more maths, we will see other more powerful ways to do these things, which can also be, see, basically, okay, first, is this clear? Yeah. But we will not do more on this now, because that's not really needed for us now. I mean, there are other things higher priority to be done. So is this okay with everyone? Any questions? Okay. Okay. What I was going to say is that when you are doing, this was nothing new really. It is just a smart bijection, right? In some sense, but yeah, maybe a lot of things that we had to check. Even I had got this problem. I had a misconception, okay, major misconception. Yeah. Are there any questions? Hmm. No, but they are the same graphs. They will be the same graphs. Right. Okay. So which two things? Okay, okay. Yeah. So should I remove this tree, just the forest you want to consider, or just the tree? No, they will be the same, because in graphs, this is the misconception I had for a very long time. In graphs, what matters is what is joined with what. Okay. What is joined with what is what a graph is all about. How you draw it is just your way, is just a convenient way to see the graph. A graph is not the drawing. A graph is a set with a binary relation. Yeah. So these two are same because even with the labeling, so there's no need to confuse with the labelings also, because set theoretically, all the information that a graph asks for is what is joined with what. Okay. What are the edges? That's all a graph is. And that is the same, that information is the same here, even with the labels. Yeah. Here, the edges are, and this set theoretic formulation can be useful, especially a lot of problems in set theory, counting problems, which look like pure set theory problems, can be done by graphs if they are careful. So you can understand, right? They are the same things because that relation 3,4. So I'm just doing this. Okay. Maybe I should ideally be doing this, but then you may confuse it for ordered tuples. These are not ordered, but you can understand. You see, this information and 6,7 and blah, blah, blah. This information is the same in both. Okay. So yeah, so graph is just a set with a binary relation. Okay, you can call that, you can say a set with a symmetric binary relation where 4,5 and 5,4 are both there and so on, but not reflexive a priori. I mean, 1,1, we're not drawing loops. This. Yes, yes. So then also it will not matter if we, so this is not what we are looking at. We were actually looking at this and this as the 7, yeah, 7 and this as the roots. And then with 9, we ended up joining with 3 and this is 7. So we get the same thing still, obviously. Again, that information of what are the, which two things are related is the same. Yeah. Mm. Mm. Which left edge? Yeah. Yes. Yeah, that matters because 9 is related to 7 and 9 is related to 3. So they are different edges. But I think you meant something else. Okay, no, but that's a different notion. Yeah, no, that does not matter here. Yeah, for us that will not matter. Yeah, so but so then that's a different notion. That's what is known as an ordered tree. Okay, uh, then there it matters. But here these are the same things. Ah, yes, yes. Okay, okay, yeah. That's right. Yeah, there it matters, and that then that's important in a lot of cases. But yeah, here it's the same thing. Yeah, that's right. Okay, so this is important to understand. Um, yeah, that a tree is just a graph is just about what is joined with what. Yeah, but however, this concept is also very. But what this is not the graph. This is actually a drawing of a graph, and soon that will start mattering. This is what is called an embedding of a graph in the plane. Yeah, we are drawing the graph in the plane and none of the edges are overlapping. So it's a true embedding, right? No two edges. So if you consider this as an actual path from here, as an actual solid path, continuous solid path from 9 to 7, then this is an edge and 8, 7 is an edge. And these edges are not sharing any common lines. Right? So it's like they're truly drawn in the plane without any loss of information. Yeah, but there are some graphs which you cannot draw like this, right? There's some graphs like this. Now, no matter how you try to draw the next two, or maybe one you can draw maybe, but Yeah, so this you can draw, and maybe this also you can draw. But then if you want to join this and this, there's no way you can draw it without overlapping with some other edge, right? So then that is not that we say is not a true drawing in the plane. That is because, right, there's a confusion here, right? So then that we say has to be drawn in 3D. So which graphs can be drawn in 2D, or simply put, which graphs can be drawn so that the edges don't intersect? uh, they are called planar graphs, and they are very important both in algorithms, and a lot of problems for general graphs are hard, but for planar graphs they are doable, and so on. We'll see something about planar graphs later. Yeah, so that's it for today. What a little bit more I was going to say is that what we are doing can be seen as number of spanning trees of the complete graph. Yeah, so when we just say number of trees on n vertices, right, you can look at it like this also: number of spanning trees on the complete graph, on n vertices, right? Because, well, complete graph of n vertices here, so obviously you can take all possible, means if you take the spanning all possible spanning trees, then you'll get all possible trees, right? And so the question of counting all possible trees on n vertices and spanning trees of the complete graph on n vertices is the same question, right? But the question will not remain the same if you remove this complete graph by some other interesting graph. And then the question comes, a number of spanning trees of some particular graph. Okay, that is a very interesting question, but that needs more maths. And that is not, it's not there in Douglas West. It's there in Douglas West, but it's not probably important for now. Okay, so we'll not do it. Okay. So given some other graph, how many trees you can make which use edges only from that graph? Okay, is there a formula for that? And given some parameters of the graph and so on, that needs a very interesting maths of determinants, and maybe we can, for the math people at least, we can explore determinants and matrices via that route. That's very that will be a very unique topic. I have to also think of how to do it, but it will be good. Okay, so yeah, that's it for today. I plan to do a 1 hour class today.